Hello and welcome to this presentation about searching algorithms. In particular, we're going to be concentrating on linear searches and binary searches because they're the ones that are mentioned in the VCE Computing study design. Our learning intention is that students can identify linear and binary searches and understand how each one works. First of all, we need to start with an understanding of what a searching algorithm does. Like, what is the point of a searching algorithm? Obviously, it searches, but what does that actually mean in explicit terms? Well, it means that we can specify if a specific value, target, exists in a data set. So we're looking for a needle in a haystack. So does this needle exist in this haystack? And we'll normally return the array of where we found it. We're talking about, sorry, not the array, the index of where we found it in the array. And normally we're searching a one-dimensional array for the purpose of the study design. As I said earlier, we are concerned with a linear search and we are concerned with a binary search. So let's start off with a linear search. A linear search is much like the woman in this photo playing the game with the cups, and what she's going along is she's lifting each cup in turn, looking, and she's comparing the value under it with the value that she wants. So the value that she wants is there's a ball under it. So she lifts up the first one and the value is no ball. No ball until she gets to it. Once she gets to it, she's actually going to break out and she's not going to check anymore because once she's found it, there's no point. So, in computing terms, what are the rules here? Well, we start at the first element of the array. That'll be the element with the index of 0. We compare the current element with the target value. So what's in that spot? Is it what we're looking for? If it is, we're just going to return the index and then we're going to break out of the program or break out of the for loop. If the element does not match, we just move to the next element. So index of 0, index of 1, index of 2. We continue until the target is found or the end of the array is reached. And this is your only option out of these two if the data is not sorted. So here is a program. This is in pseudocode, of course. So here we've got the numbers and we've got an array with those numbers there. I feel like there's about 7 numbers there. We're looking for number 23, and to start off we're saying found, the boolean, is false. That would probably be a better name if it was is found, or maybe is present. So we're going to have a for loop with our index called index, range 0 to the length of the numbers, and we're going to go through and say if numbers with an index of that equals the target, so we're checking each one. Now, if it does match, then we're going to say found is true, we're going to print that we found it, and we're going to break. Whoops. But when we get to the end, we're going to say if found equals false, then we're going to print it wasn't found. So if the boolean is still in the state of false, well, then it wasn't there. Let's have a look at this in action. So I actually have this open in another tab. No, turns out I don't. There it is. So I'm just going to reset that. So there's our numbers. You'll see that they're not in order. So let's search for, I'm just going to use a random number. Let's search for 52. Now I actually don't think 52 is in here, but let's have a look. See, it's searching each one. Oh, there you go. And once it got to 52, it stopped searching. So that's how that worked. I'm just going to run it another time. Just so let's pick something that I don't think is in there. I'm going to search for 23. I actually should have checked. There we go. It's checking everything. Yep, there we go. And looking ahead, it's not going to find it. Yep. And so it says down here, it was not found in the array after 20 comparisons. So there you go. That's a result of false. So that's how a linear search works. Now, how does a binary search work? Well, the best example for a binary search is a guessing game. So we're trying to guess a number between 1 and 15. So first thing we do, if we're at all intelligent about this, is we start with 8. Well, it turns out that 8 was too low. So now we know we're looking for something between 9 and 15. And so we're going to pick in the middle of that, which is 12. Now, is 12 right? Well, no, that's too high. So now we know that it's not 12. It could be 13. It could be all the way down to 9. We're going to pick 10 as a number in the middle, and then we're going to go from there. So you're basically halving the range that you're looking at. So let's have a look at this. We're thinking of a game where you have to guess a number between 1 and 100. So let's guess 50. Oh, 50 is too high. So obviously I'm not going to guess 50 or higher. My range is now 1 and 49. So then I pick the middle number between 1 and 49, and I probably want to round it. When I divide it by 2, I probably want to make sure I'm rounding it, because if I'm getting strictly between the two, I might be ending up with a float rather than an integer, and your indexes are all integers. Excuse me. Oh no, I thought my washing machine was going to need my intervention, but it looks like it'll live to fight another day. Actually, you know what? I'm going to see my washing machine. Okay, I'm back from visiting the washing machine. So now we ask, is it 25? Because we're getting the middle number between 1 and 49. No, that's too low. So now we're guessing between 26, because it's not 25, and 50. Now it's not 50, I've miswritten that, that's actually 49. So 26 to 49. So we ask the number in the middle, is it 38? Well, that's too high. Well, now it's between 26 and 37. And so we go. Now, this actually feels a bit laborious, but it's actually tremendously efficient. Here is our example. So what we do is we say, while the smallest possible number is less than or equal to the greatest possible number. So basically, while the two boundaries are apart, what we're going to do is we're going to pick the middle, which is the smallest plus the largest divided by 2, and we're actually using the floor so that we're rounding that down. We could round it up, it wouldn't really matter. Then we're saying, well, we're going to take that middle number and we're going to check the spot on the array that matches that middle number. And if it matches, if our number magically is 50, then it returns it and says, yep, beautiful, that's the index, we found it. Otherwise, if the number we're checking is smaller than the target, or if the spot in the middle is smaller than the target, we're going to change the bottom, the smallest possible number. So if we ask 50 and it says, no, it's higher than 50, well, now our smallest possible number is 51. Now, if it said it was lower than 50, then our largest possible number is now going to be 49. So we're resetting one of the boundaries when we find out if it's too high or too low. And then we keep going. And we go all the way through, and then if we get to the end and it hasn't returned something, that means that the target isn't found, and we're returning a value of -1. So, how does it work? Well, we have to start with a sorted array. We identify the middle element, so 50 in this game. We compare our target, what we're looking for, with the middle element. If the target matches, yep, bingo, happy days. If the target is less than the middle element, search the left half. So if it's less, 49 and down. If it's greater, 51 and up. And repeat until the target is found or the search interval is empty. So we might get to the point where we're getting down to two numbers, and then we just go, oh, okay, there's nothing left. There's no spots left to check. It mustn't be there. So let's go and have a look at the demonstration of this. So you'll notice in this one that, first of all, the arrays are labelled, so array 0 through to array 19, the indexes, sorry, and that they are in order. This will not work if they're not in order. So let's find a number to search for. Now, I'm going to search for 40 because I want to not find it. So I start my search. There it is. So it looks in the middle, and it says 39. Okay, so these are all the numbers that are still in play. 42 through to 88 are still in play. Okay, 42 is the only one that's still in play, and it was not found. All right, let's find one. So we're going to reset. Let's find something down here that should be a bit hard to find, actually, 23. So it should actually take about 4 steps to find 23. Let's have a go. So 39, well, we know it's smaller than 39. So that's what's left. We pick the middle one. Is it 28? Well, we know it's smaller than that. So we pick as close as we can to the middle. Nope. And yes, we found it. So we in fact did it in 4 steps. Now this actually works really well with large number sets. You'd be surprised how quickly you can get through it with a much larger set of numbers. So, in terms of efficiency, I don't really understand this. This is too mathematical for me, but A linear search is really not very efficient unless you happen to chance into it. Imagine if you had to check, if these things were lined up a mile long and you had to go through and check every one. It's pretty much hit or miss whether you're efficient or not. And on average case, it's 0 bracket n. Couldn't really tell you what that means. A binary search is actually dramatically more efficient over anything but a very small number set. So let's find out what we know already. A linear search requires the data to be sorted before the search can begin. Well, that's false. In fact, the beauty of a linear search is that it doesn't care about data sorting. Binary search works by repeatedly dividing the search range in half. Well, absolutely, that's actually its very definition. In the worst case scenario, a linear search for an item in a list of n elements will take that time. Hang on, no, that's wrong, because that one with the log is in fact is the binary search, not the linear search. Yep. A binary search is generally faster than a linear search for large sorted data sets. Yeah, that's absolutely true. Binary search requires more comparisons than linear search when the list size is very small. Yeah, that would generally be true. The midpoint in a binary search is typically calculated as low plus high divided by 2. Yep. And in a binary search, if the target is greater than the middle element, the algorithm searches the left half of the remaining list. Well, that's a trick. That's false. Because in actual fact, it would be if it's greater than, it would be the right half. So, 50 and up if we were going up to 100. And a linear search is the only option when you need to find an item in an unsorted array. Yes, that's absolutely true. So that is the end of the presentation. I hope you found that useful. You can find those demonstrations on 42 Penguins if you're looking for them. And of course, there's information about this on the wiki as well.